You can find it in the rainforest, on the frontiers of medical research, in the movies, and it's all over the world of wireless communications. One of nature's biggest design secrets has finally been revealed.
My God, of course, it's obvious.
It's an odd-looking shape you may never have heard of, but it's everywhere around you. The jagged, repeating form called a fractal.
They're all over in biology. They're solutions that natural selection has come up with over and over and over again.
Fractals are in our lungs, kidneys, and blood vessels.
Flowers, plants, weather systems, the rhythms of the heart, the very essences of life.
But it took a maverick mathematician to figure out how they work.
I don't play with formulas, I play with pictures. And that is what I've been doing all my life.
His was a bold challenge to centuries-old assumptions about the various forms that nature takes.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
Making the invisible visible, finding order in disorder. What mysteries can it help us unravel? Coming up next on Nova, hunting the hidden dimension. Benoit Mandelbrot, whose work had inspired that innovation, was someone who prided himself on standing outside the mainstream.
I can see things that nobody else suspects until I point out to them. Oh, of course, but they haven't seen it before.
You can see it in the clouds, in the mountains, even inside the human body.
The key to fractal geometry, and the thing that evaded anyone until really Mandelbrot sort of said this is the way to look at things, is that if you look on the surface, you see complexity, and it looks very non-mathematical. What Mandelbrot said was that think not of what you see, but what it took to produce what you see.
It takes endless repetition, and that gives rise to one of the defining characteristics of a fractal, what mathematicians call self-similarity.
The main idea is always, as you zoom in and zoom out, the objects look the same.
If you look at something at this scale, and then you pick a small piece of it and you zoom in, it looks very much the same.
The whole of the fractal looks just like a part, which looks just like the next smaller part. The similarity of the pattern just keeps on going. After the war, Mandelbrot got his PhD. He tried teaching at a French university, but he didn't seem to fit in.
They say, well, I'm very gifted but very misled, and I do things the wrong way. I was very much a fish out of water. So I abandoned this job in France and took the gamble to go to IBM.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description, there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end. And now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said was, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side
I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece.
over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long a yardstick is and how much patience you have. If you measure the coastline of Britain with a 1-mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1-foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number.
Because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, 1 dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.
Mandelbrot's fresh ways of thinking were made possible by his enthusiastic embrace of new technology. Computers made it easy for Mandelbrot to do iteration, the endlessly repeating cycles of calculation that were demanded by the mathematical monsters.
The computer was totally essential. Otherwise, have taken a very big, long effort.
Mandelbrot decided to zero in on yet another of the monsters, a problem introduced during World War I by a young French mathematician named Gaston Julia.
Gaston Julia, he was actually looking at what happens when you take a simple equation and you iterate it through a feedback loop. That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula, get another number out. And you keep iterating that over and over again. And the question is, what happens when you iterate it lots of times?
The series of numbers you get is called a set, the Julia set. But working by hand, you could never really know what the complete set looked like.
There were attempts to draw it, doing a bunch of arithmetic by hand and putting a point on graph paper.
You would have to feed it back hundreds, thousands, millions of times. The development of that new kind of mathematics had to wait until fast computers were invented.
At IBM, Mandelbrot did something Julia could never do: use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
My first step was to just draw mindlessly a large number of Julia sets. Not one picture, hundreds of pictures.
Those images led Mandelbrot to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
They intersect at certain areas, and it's got like a,
And they have little curlicues built into them.
Black, beetle-like thing crawling across the floor.
Seahorses, dragons.
Something similar to my hair, actually.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, 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 you're zooming in, you're zooming in, and pop. Suddenly it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
But when the Mandelbrot set was first published, mathematicians, for the most part, reacted with scorn.
In the Mathematical Intelligencer, which is a gossip sheet for professional mathematicians, there were article after article saying he wasn't a mathematician, he was a bad mathematician, it's not mathematics, fractal geometry is worthless.
The eye had been banished out of science. The eye had been excommunicated.
His colleagues, especially the really good ones, pure mathematicians that he respected, they turned against him.
Because, you get used to the world that you've created and that you live in, and mathematicians had become very used to this world of smooth curves that they could do things with.
They were clinging to the old paradigm, when Mandelbrot and a few people were way out there bringing in the new paradigm. And he used to call me up on the telephone late at night because he was bothered, and we'd talk about it. Mandelbrot was saying, this is a branch of geometry just like Euclid. It offended them. They said, no, this is an artifact of your stupid computing machine.
I know very well that there is this line that fractals are pretty pictures, but are pretty useless. Well, it's a pretty jingle, but it's completely ridiculous.
Mandelbrot replied to his critics with his new book, The Fractal Geometry of Nature. It was filled with examples of how his ideas could be useful to science. Mandelbrot argued that with fractals, he could precisely measure natural shapes and make calculations that could be applied to all kinds of formations, from the drainage patterns of rivers to the movements of clouds.
So this domain of growing living systems, which I, along with most other mathematicians, had always regarded as pretty well off limits for mathematics and certainly off limits for geometry, suddenly was center stage. It was Mandelbrot's book that convinced us that this wasn't just artwork. This was new science in the making. This was a completely new way of looking at the world in which we live that allowed us not just to look at it, not just to measure it, but to do mathematics and thereby understand it in a deeper way than we had before.
As someone who's been working with fractals for 20 years, I'm not going to tell you fractals are cool. I'm going to tell you fractals are useful. And that's what's important to me.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals was a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable and my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was, frankly, an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals, experimentally, I came up with a very wideband antenna. And then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
We're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get cheaper cost and smaller size for all the complex telecommunication needs we're having.
Once you realize that a shrewd engineer would use fractals in many, many contexts, you better understand why nature, which is shrewder, uses them in its ways.
They're all over in biology. They're solutions that natural selection has come up with over and over and over and over again.
One powerful example, the rhythms of the heart. Something that Boston cardiologist Ari Goldberger has been studying his entire professional life.
The notion of sort of the human body as a machine goes back through the tradition of Newton and the machine-like universe. So somehow we're machines, we're mechanisms, the heartbeat is this timekeeper. Galileo was reported to have used his pulse to time the swinging of a pendular motion, so that all fit in with the idea that the normal heartbeat is like a metronome.
But when Goldberger and his colleagues analyzed data from thousands of people, they found the old theory was wrong.
This is where I showed the heartbeat time series of a healthy subject. And as you can see, the heartbeat is not constant over time. It fluctuates, and it fluctuates a lot. For example, in this case, it fluctuates between 60 beats per minute and 120 beats per minute.
The patterns looked familiar to Goldberger, who happened to have read Benoit Mandelbrot's book.
When you actually plotted out the intervals between heartbeats, what you saw was very close to the rough edges of the mountain ranges that were in Mandelbrot's book. You blow them up, expand them, you actually see that there are more of these wrinkles upon wrinkles. The healthy heartbeat, it turned out, had this fractal architecture. People said, this isn't cardiology, we do cardiology if you want to get funded. But it turns out it is cardiology.
Goldberger found that the healthy heartbeat has a distinctive fractal pattern, a signature that one day may help cardiologists spot heart problems sooner.
Please look around the screen for me. All right, Cooper, we're going to do the calibration.
At the University of Oregon, Richard Taylor is using fractals to reveal the secrets of another part of the body, the eye.
What we want to do is see what is that eye doing that allows it to absorb so much visual information. And so that's what led us into the eye trajectories. Under the monitor is a little infrared camera which will actually monitor where the eye is looking, and it actually records that data. And so what we get out is a trajectory of where the eye has been looking.
Oh, it's interesting how they go around the patterns.
And so the computer will get out this graph, and it will look, have all of these various little structure in it. And it's that pattern that we zoom in, we tell the computer to zoom in on and see the fractal dimension.
The tests show that the eye does not always look at things in an orderly or smooth way. If we could understand more about how the eye takes in information, we could do a better job of designing the things that we really need to see.
A traffic light. You're looking at the traffic light, you've got traffic, you've got pedestrians. Your eye is looking all over the place, trying to assess all of this information. People design aircraft cockpits, rows of dials and things like that. If your eye is darting around based on a fractal geometry, though, maybe that's not the best way. Maybe you don't want these things in a simple row. We're trying to work out the natural way that the eye wants to absorb the information. Is it going to be similar to a lot of these other subconscious processes? Body motion. When you're balancing, what are you actually doing there? It's something subconscious and it works, and you're stringing together big sways and small sways and smaller sways. Could those all be connected together to actually be doing a fractal pattern there? More and more physiological processes have been found to be fractal.
Not everyone in science is convinced of fractal geometry's potential for delivering new knowledge. Skeptics argue that it's done little to advance mathematical theory. But in Toronto, biophysicist Peter Burns and his colleagues see fractals as a practical tool, a way to develop mathematical models that might help in diagnosing cancer earlier.
Detecting very small tumors is one of the big challenges in medical imaging.
Burns knew that one early sign of cancer is particularly difficult to see: a network of tiny blood vessels that forms with the tumor. Conventional imaging techniques like ultrasound aren't powerful enough to show them.
We need to be able to see structures which are just a few tenths of a millionth of a meter across. When it comes to a living patient, we don't have the tools to be able to see these tiny blood vessels.
But ultrasound does provide a very good picture of the overall movement of blood. Is there any way, Burns wondered, that images of blood flow could reveal the hidden structure of the blood vessels? To find out, Burns and his colleagues used fractal geometry to make a mathematical model.
If you have a mathematical way of analyzing a structure, you can make a model. What fractals do is they give you some simple rules by which you can create models. And by changing some of the parameters of the model, we can change how the structure looks.
The model showed the flow of blood in a kidney, first through normal blood vessels, and then through vessels feeding a cancerous tumor. Burns discovered that the two kinds of networks had very different fractal dimensions.
Instead of being neatly bifurcating, looking like a nice elm tree, the tumor vasculature is chaotic and tangled and disorganized, looking more like a mistletoe bush.
And the flow of blood through these tangled vessels looked very different than in a normal network. A difference doctors might one day be able to detect with ultrasound.
We've always thought that we have to make medical images sharper and sharper, ever more precise, ever more microscopic in their resolution to find out the information about the structure that's there. What's exciting about this is it's giving us microscopic information without us actually having to look through a microscope.
You can see it rises up as the bubbles.
We think that this fractal approach may be helpful in distinguishing benign from malignant lesions in a way that hasn't been possible up to now.
It may take years before fractals can help doctors predict cancer, but they are already offering clues to one of biology's more tantalizing mysteries. Why big animals use energy more efficiently than little ones? That's a question that fascinates biologists James Brown and Brian Enquist and physicist Jeffrey West.
There is an extraordinary economy of scale as you increase in size.
An elephant, for example, is 200,000 times heavier than a mouse, but uses only about 10,000 times more energy in the form of calories it consumes.
The bigger you are, you actually need less energy per gram of tissue to stay alive. That is an amazing fact.
And even more amazing is the fact that this relationship between the mass and energy use of any living thing is governed by a strict mathematical formula.
So far as we know, that law is universal, or almost universal, across all of life. So it operates from the tiniest bacteria to whales and sequoia trees.
But even though this law had been discovered back in the 1930s, no one had been able to explain it.
We had this idea that it probably had something to do with how resources are distributed within the bodies of organisms as they varied in size.
We took this big leap and said all of life in some way is sustained by these underlying networks that are transporting oxygen, resources, metabolites that are feeding cells. Circulatory systems and respiratory systems and renal systems and neural systems. It was obvious that fractals were staring us in the face.
If all these biological networks are fractal, it means they obey some simple mathematical rules, which can lead to new insights into how they work.
If you think about it for a minute, it would be incredibly inefficient to have a set of blueprints for every single stage of increasing size. But if you have a fractal code, a code that says when to branch as you get bigger and bigger, then a very simple genetic code can produce what looks like a complicated organism.
Evolution by natural selection has hit upon a design that appears to give the most bang for the buck.
In 1997, West, Brown, and Enquist announced their controversial theory that fractals hold the key to the mysterious relationship between mass and energy use in animals. Now they are putting their theory to a bold new test, an experiment to help determine if the fractal structure of a single tree can predict how an entire rainforest works.
Measurements of its trunk, the next
Enquist has traveled to Costa Rica, to Guanacaste province in the northwestern part of the country. The government has set aside more than 300,000 acres in Guanacaste as a conservation area. This rainforest, like others around the world, plays a vital role in regulating the Earth's climate by removing carbon dioxide from the atmosphere.
If you look at the forest, it basically breathes. And if we understand the total amount of carbon dioxide that's coming into these trees within this forest, we can then better understand how this forest then ultimately regulates the total amount of carbon dioxide in our atmosphere.
With carbon dioxide levels around the world rising, how much CO2 can rainforests like this one absorb? And how important is their role in protecting us from further global warming? Enquist and a team of U.S. scientists think that fractal geometry may help answer these questions.
The baseline, let's try to get the height of the tree measured here.
They are going to start by doing just about the last thing you'd think a scientist would do here: cut down a balsa tree. It's dying anyway, and they have the permission of the authorities.
So Christine, as soon as you know the height of that tree, we can actually figure out the approximate angle that we need to take it down on.
Hooking a guideline on a high branch helps ensure the tree will land where they want it to.
Very good, very nice. Jose, perfecto.
Enquist and his colleagues then measure the width and length of the branches to quantify the tree's fractal structure.
8.
10.06.
No, that's 8.
6.3.
0.03.
608.
7 on the nose.
They also measure how much carbon a single leaf contains, which should allow them to figure out what the whole tree can absorb.
So if we know the amount of carbon dioxide that one leaf is able to take in, then hopefully using the fractal branching rule, we can know how much carbon dioxide the entire tree is taking in.
Their next step is to move from the tree to the whole forest.
All right, this is good.
13.2, 3.3 R.
We're going to census this forest. We're going to be measuring the diameter at the base of the trees, ranging all the way from the largest trees down to the smallest trees.
3 meters above the ground.
And in that way, we can then sample the distribution of sizes within the forest.
It's 61.8 centimeters.
Even though the forest may appear random and chaotic, the team believes it actually has a structure. One that, amazingly, is almost identical to the fractal structure of the tree they have just cut down.
The beautiful thing is that the distribution of the sizes of individual trees in the forest appears to exactly match the distribution of the sizes of individual branches within a single tree.
If they're correct, studying a single tree will make it easier to predict how much carbon dioxide an entire forest can absorb.
So is this is the tree plot, right?
Yeah. The cool thing is that if you look at the tree, you see the same pattern amongst the branches as we see amongst the trunks of the forest.
Very nice.
Just as they'd predicted, the relative number of big and small trees closely matches the relative number of big and small branches.
It's actually phenomenal that it is parallel there. The slope of that line for the tree appears to be the same for the forest as well.
So I guess it was worth cutting up the tree.
It was definitely worth cutting up the tree.
So far, the measurements from the field appear to support the scientists' theory that a single tree can help scientists assess how much this rainforest is helping to slow down global warming.
By analyzing the fractal patterns within the forest, that then enables us to do something that we haven't really been able to do before. Have then a mathematical basis to predict how the forest as a whole takes in carbon dioxide. And ultimately, that's important for understanding what may happen with global climate change.
Fractal geometry is leading to a whole new understanding, revealing an underlying order governed by simple mathematical rules.
What I thought of in my hikes through forest, that, you know, just a bunch of trees of different sizes, big ones here, small ones there, looking like it's sort of some arbitrary, chaotic mess, actually has an extraordinary structure.
A structure that can be mapped out and measured using fractal geometry.
What's absolutely amazing is that you can translate what you see in the natural world in the language of mathematics. And I can't think of anything more beautiful than that.
Math is our one and only strategy for understanding the complexity of nature. Now, fractal geometry has given us a much larger vocabulary. And with the larger vocabulary, we can read more of the book of nature.
All that mattered was that the body was dead.
What does one of America's most iconic figures have to do with the bones in the basement? In 1752, he'd won worldwide fame when he proved that lightning was not an act of God, but in fact, electricity.
Franklin was passionate about science. He was intellectually curious, and there was no subject that didn't pass his attention. He was here in London pursuing experiments related to electricity. He looked at better ways to make clocks and improve bifocal lenses. He even created a flexible steel catheter for his brother.
And he tried to find a cure for the common cold.
He believed that you needed to let out the stale air and let in the fresh air. Here in his rooms at Craven Street, he supposedly took an air bath where he sat around without his clothes on for a time each day and had the windows wide open so that he could take in the fresh air. Franklin thought that science could really help people, and he was always looking at ways to improve life for himself and for others.
Someone like Franklin would have been appreciative of the kind of knowledge that was being created through dissection and through experiment.
Hewson himself made significant medical advances. He discovered the lymphatic system existed not just in humans, but also in amphibious creatures and birds. He isolated fibrinogen as a key protein in the coagulation of blood, and he identified the true shape of red blood cells.
Before this, they had been known as globules, and they were thought to be spherical in nature. But Hewson used the microscope to look at them and said, why no, they're flat as Guinea. So for all of these amazing accomplishments, Hewson is currently known today as the father of hematology.
Hewson's school provided him with a thriving business to support his growing family. His classes were very popular, and pupils paid up to 10 guineas for a series of courses. By 1774, 2 years after establishing his venture, Franklin's friend and protege was considered a great success. The bones at Craven Street are symbolic of a remarkable chapter in medical history. The macabre activities of the body snatchers belie the important work that was done to create a profession based on science, logic, and evidence.
The Houston family just loves the story of the Craven Street bones. And I have to say, it's the type of story that we tell again and again around the dinner table with friends. So it's a very unique story to have attached to our name, and we just love it.
But it's also provided insight into the life and character of Benjamin Franklin.
I think that the Craven Street bone pits are part of Franklin's story, yes. I do think that the material there is a window on a particular time and place, and it really says that science was important and necessary.
I think the discovery of the Craven Street bones reveals just how reveals just how